तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, let us go on to problems of a particle moving in an electromagnetic field. This is what I would like to do next, namely look at the motion of a quantum mechanical particle in applied electric and magnetic fields. But before I do that, there was one little aspect which I omitted to mention. We looked at the problem of a particle in a potential well, like an infinite well, like in a box, and then I mentioned something about a finite well. We looked at the problem of the delta function well, but we did not look at barrier problems. So let me briefly mention scattering from a potential barrier and then go on to the problem of a charged particle in an electromagnetic field. So this is scattering from a potential barrier. Again in one dimension. If time permits, we will talk about 3-dimensional scattering subsequently. And the kind of situation I have in mind is as follows. You have a potential which is really a well, so a barrier in the sense that here is V of x and here is x, and let us assume that the potential is 0 as x tends to minus infinity, and as x tends to plus infinity it is some finite value, not 0. So a little hill of some kind, and this is some value V0, asymptotic value V0, and this is 0. The question is, what does a quantum mechanical particle put in such a potential do? Okay. Classically, of course, you see that the energy can never be, total energy can't be negative. You could have a total energy which is this much, for example, then a particle coming along with this kind of energy would climb up to this point and roll back, it would go back. So it would essentially get reflected off this potential and go back. This is what would happen classically for a classical particle. Now quantum mechanically the particle is described by a wave function, position space wave function, and then the question is, what happens if you shoot a particle in this direction and what would it do? What happens in the quantum case is that if the total energy is less than V0, then the particle comes along, a portion of this wave function actually exists in this region but dies down exponentially and then is reflected back. But there would be, exactly as in total internal reflection, the incident wave would be reflected back and there is no transmission as such. Classically, if you have an energy greater than V0, a particle would come along and move in this region with reduced velocity because there is some potential energy, the total energy is conserved and therefore the kinetic energy would decrease, and with reduced speed it would move in this direction. It would overcome the potential barrier and go across to plus infinity with a reduced velocity. Quantum mechanically something interesting happens. A particle with energy greater than V0 is an incident wave, a portion of it is transmitted and a portion of it is reflected back on this side, and the amount that is transmitted, the ratio of intensities will tell you that there is a transmission coefficient and there is a reflection coefficient. So let us work that problem out. So we start by saying I am going to look at E greater than V0 because that is the case of interest. E less than V0 is a trivial case, we can solve that. Once we do this we can easily find out what E less than V0 would do, and then ask what does the wave function do. Well, asymptotically from this side the incident wave is a plane wave of some fixed momentum, a free particle. So its wave function incident wave function, I am only looking at the stationary wave functions now, is proportional to e to the power ikx, where as you can see 2me by h cross squared equal to k squared, or E is h cross squared k squared over 2m, p squared over 2m. This is all that I have written. So there is a certain wave number associated with the incident wave, and that is k, and the wave function is proportional to e to the ikx. Now this is not a normalizable wave function, it is a plane wave, therefore it is not normalizable. The extent of this thing is minus infinity to infinity, the energy is certainly greater than 0, and it is not a bound state, it is a free wave moving. By our convention, a wave moving to the right would have a space dependent part of the wave function would be e to the plus ikx, moving to the left would be e to the minus ikx. Okay. So this is what the incident wave does, and now we ask what does it do on that side very far out. On the right hand side, the transmitted wave function, this is equal to some constant, I do not care what it is, some a e to the power I k prime x, and what is k prime? 2m e minus v naught over h cross squared equal to k prime squared. Because we write the Schrodinger equation down at this point very far away there, you write the normal time independent Schrodinger equation, there is an E on the right hand side for h psi is E psi, but on the left hand side there is also a potential V naught. You bring this over to this side, and then you have E minus V naught as the available energy, if you like. E is the energy eigenvalue of this particle. Therefore you can see k prime is reduced in magnitude from the original wave number k. This is like a light wave moving from one medium to another. Clearly there is a refractive index, and then the effective speed decreases. What is the wave function on this side? There some of it is reflected, and what does that reflected wave do? Reflected wave function, this thing is equal to some constant, need not be the same constant, some b, do not care, times e to the power minus ikx, because it is moving in this medium here asymptotically very far away, there is no potential, so the wave number is once again k, but it is moving in the other direction, and therefore on this side it is b e to the minus ikx. So this says that as x tends to minus infinity, psi of x is equal to e to the power ikx plus b e to the power minus ikx, apart from an overall normalization constant of some kind. We take that to be unity, for example. And as x tends to plus infinity, psi of x equal to e to the power a e to the power I k prime x. Now what is the current? What is the probability current? Well, for a plane wave the probability current is easy to find. So probability current everywhere is h cross over 2mi, and if you recall the expression we wrote last time, it is psi star delta psi over delta x minus psi delta psi star over delta x. That was our expression for the probability current. For a plane wave, if psi is e to the ikx, apart from some constant, then this current equal to, there is an h cross over 2mi, and this is going to give you e to the minus ikx, this is going to give you an ik when you differentiate, and the exponentials cancel, and there is an extra minus here for the psi star, so it gives you 2ik, and the 2i cancels and you get h cross k over m. which is not unreasonable. That is the momentum divided by the mass, that is like the velocity if you like. Okay. This is what you would expect the current to be for a particle of unit charge, for instance. So I define the transmission coefficient equal to the ratio of the probability current, the transmitted probability current to the incident probability current. That is a reasonable way to define the transmission coefficient. So transmitted probability current to the incident so one takes this portion of the wave function, finds the current and divides it by the incident current, which is h cross k over m. And when you take this function and find the transmitted probability current, there is a psi and a psi star, so there is going to be an A and an A star as well multiplying, and therefore it is not difficult to see that this is equal to k prime over k mod A squared, because this is going to come by differentiating this plane wave, and then there is a mod A squared, and this h cross over m factor cancels out on both sides. So the physical meaning of this arbitrary constant A multiplying the transmitted wave is that the modulus of A squared is essentially the transmission coefficient, multiplied of course by the ratio of wave numbers in the two media. Similarly, the reflection coefficient is equal to reflected probability current divided by incident and what is that equal to? Well, you have now got to take this guy, that is the reflected wave, and this is the incident wave here, so it is easy to see that this is just mod B whole squared. Okay. Now of course probability must be conserved. Initially if you normalize your wave function such that the total probability is 1, when you add the reflected and transmitted waves you should again get 1, part of it goes through there, part of it comes back here. So it follows, so I will call this T and I will call this R. So it follows that T plus R must be equal to 1 always. So that relates mod A squared to mod B squared, and then to actually find out what these guys are requires you to solve the Schrodinger equation with that specific form of the potential and then find out what happens asymptotically. You are given the asymptotic values, but those coefficients A and B, one of them would be determined in terms of the other up to a phase, and that can only be found if you actually tell me the shape of the potential, if you tell me what is in between. So let us look at an extremely simple case where the potential is very easy to write down. So the special case we are going to look at, when do we have absorption? Let me explain. When we have absorption, when we have perfect reflection, we have total internal reflection, we will not have absorption in this problem at all unless there is something that is going on, a reaction that is going on that is causing particles to disappear. So if you shoot for example a beam of electrons or neutrons at a nucleus and the nucleus absorbs some of it, then the total incident flux of neutrons disappears, it goes into the nucleus, then you indeed have a real absorption coefficient and part of it is scattered, and this is going to be taken into account by making the potential complex so that some probability disappears, probability mass disappears, otherwise you will have conservation of probability, right. So you need a complex potential, and this is called the optical potential method, where you actually pretend the potential is complex but its imaginary part is related to the absorption coefficient, because something else happens, another reaction takes place, otherwise it is pure scattering. So in these problems you have pure scattering, which is why R plus T is exactly equal to 1, there is no leakage or loss anywhere. So the potential I have in mind is the simplest of all, so here is x, here is V of x, and let us just say it is 0 all the way up to 0, and then it is a barrier and you have a V naught. Now we can write down the solution to the Schrodinger equation trivially, because there is no potential anywhere here. Therefore in this region 1 and this is region 2, in 1 the wave function psi of x is exactly equal to e to the I k x plus b e to the minus I k x is exactly equal to that. There is no approximation involved here, because there is no potential here, it is just a free particle. Some of it is getting reflected back, and that is the b portion. And then in 2 psi of x is exactly equal to a e to the power I k prime x, no approximation involved here, and that is it. Now how are you going to fix a and a prime, a and b? K and k prime are known to you because you know what E is and you know what V naught is. Every E greater than V naught is an allowed solution, allowed eigenvalue. You have a continuous spectrum. So E and V naught are given numbers. How are you going to find, so you know K and K prime, how do you find A and B now? Well, you also have this normalization condition, you know that T plus R must be equal to 1, so we can write that down, mod A squared times K prime over K plus mod B squared has got to be equal to 1, that is fine. But how are you going to find A? You have to use the continuity of the wave function at this point 0. So you have to use the fact that psi of 0 minus equal to psi of 0 plus. So coming from one side and the other side they must be equal, which implies that 1 plus B is equal to A. So you have that relation. You also need a relation for the complex conjugates, and that you find by saying that the derivatives of the potential on both sides have to be continuous, because after all what does your Schrodinger equation tell you? It says minus h cross squared over 2m psi double prime of x plus v of x psi of x is equal to e psi of x, and this function is continuous. V of x has a finite discontinuity, it is a finite discontinuity. So V double prime has a finite discontinuity to compensate for this guy here, not an infinite discontinuity. So the wave function's slope must also match, the slopes would have a cusp, so that psi double prime, the curvature, would be discontinuous. So you also need to impose psi prime of 0 minus equal to psi prime of 0 plus. When you do that you have enough conditions to find A and B simultaneously, and then you can check that this relation T plus R is 1 is automatically satisfied. So I leave you to work the rest of this algebra out. These two conditions are enough to determine A and B, and then verify that the reflection plus transmission coefficients is indeed 1. Now for Purnima's questions in a slightly different guise, what happens if E is less than V naught in this problem? What happens if this is your total energy? That is also an allowed value of the energy. What would happen? What would happen in this region? This would still be the form of the wave function, but look at what K prime is. K prime squared is 2m E minus V naught divided by h cross squared. So K prime is the square root of this guy, and what happens if E is less than V naught? It becomes imaginary, right, and therefore I K prime becomes a negative number, and then the wave function here, so you have wave here, but once it comes here it dies down exponentially. So although in this case, and you can check this out, the transmission coefficient is 0, nothing goes through asymptotically, as x goes to plus infinity there is no wave function, no flux of particles. However, there is a penetration into this barrier and it dies down exponentially fast with an exponent which is essentially square root of 2m V naught minus E over h cross. So that is the inverse of that is a length scale, yeah.
Normalization, what does it mean?
You can put this whole thing in a box, a huge box, and normalize it in that box. It is not normalizable because it's e to the ikx is not a member of L2 from minus infinity to infinity, but it is a member of L2 from minus L to plus L if you like. And then of course you would argue by saying, oh, but be careful, if I put it in a huge box minus L to plus L, then the momentum gets quantized, the wave number gets quantized because it has got to satisfy boundary conditions, right. So this is called box normalization. I would let the box go to infinity, then the levels become essentially continuous. That is one way of doing it. A more rigorous way of doing it would be to say I cannot find a sharp momentum eigenstate, a plane wave is a fiction. So I find a wave packet localized about some wave number k0, maybe a Gaussian wave packet. I shoot that and then it comes back, and I could do the same thing completely for a superposition of waves. If I can do it for one, the whole thing is linear. So that is the second way to do it, namely do everything with wave packets, the rigorous way to do it. This is a lot of complication. So one chooses box normalization generally. Okay. So the physical point is not, the important thing is not the overall factor but the relative factors here. One is to B, that's the, and then is to A. Those are the relative strengths or intensities that we are worried about. So I leave you to work out the rest of this problem, including the penetration here. And this is actually true even in classical electromagnetic theory. When you have total internal reflection of a light ray which is inside a denser medium greater than the critical angle of incident, at incident angle greater than critical angle, it goes up, it gets reflected in this fashion in the denser medium, but there is an evanescent wave in the other medium. So there is something which exponentially dies down. Only in ray optics is it strictly internal reflection. Otherwise in wave optics there is a little bit of penetration into the other medium. That is a property of waves, and the same thing goes on here. So as you get closer and closer, as you get this dies down, as E is smaller and smaller, it dies down faster and faster. Okay. In fact you could go now to the limit of asking, what if I took this barrier and cut it off after some time. So what if I did this? What if this was my barrier? So here is 0, here is A. What is going to happen now to an incident particle which is coming in with an energy like that? There is going to be a transmission there. But in this region where there is a potential V0, the effective wave number is different from what it is in the free case. So it is like something with a light ray passing in air through a slab of glass and back into air. That is exactly what is going to happen. And now to solve this problem, in this region you would say the wave function is of the form e to the I kx plus b e to the minus I k prime x kx once again. What would you say it is here? Some c e to the I kx moving asymptotically in this direction. And what would it be here? In this region, in region 2, it would be of the form some d e to the I k prime x plus e to the minus I k prime x. There is no reason why you can't have both out there. It would be a superposition, and then you would equate the wave function and its derivative here, the wave function and its derivative there on that side, and that is how you determine these constants. What if I made A0 and increased the height V0 of this barrier such that the product remains finite? You got a delta function. What would happen then? So I have a barrier. We did the problem of a bound state in a delta function. It was a negative delta function, but now I got a delta function barrier. So V of x equal to plus lambda delta of x. What would the answer be now? Would there be a transmission coefficient? Yes. You can solve this by first solving the problem of V0 and A with a finite V0 A, and then taking the limit in which V0 tends to infinity, A tends to 0, such that the product is finite and related to lambda. and indeed there is a transmission coefficient in this case. So any incident wave which comes along will be partially transmitted, partially reflected, and you can compute the transmission and reflection. What kind of boundary condition would you put there? If instead of looking at finite barrier of finite width and then letting the width go to 0 and the height go to infinity, I start with a delta function. What kind of boundary conditions would you put there? The wave function would be continuous, but if you go back to the Schrodinger equation, this has got an infinite discontinuity at the origin because it is a delta function. Therefore this has an infinite discontinuity because that itself is continuous. This has got to compensate for that. If psi double prime has an infinite discontinuity, it means psi prime has a finite jump, and therefore psi has a cusp at that point. You cannot in this problem equate derivatives on both sides. You can equate the wave function on both sides, but then you must integrate this equation from minus epsilon to plus epsilon, and then the discontinuity in the first derivative would be related to the strength of the delta function here, and therefore you can again check independently whether the finite barrier problem correctly goes to the delta function limit or not. Again, that is going to be given to you as an exercise. These barrier penetration problems are crucial in many areas and have played a very big role in applications of quantum mechanics. What I want to turn to next is, yeah.
So when the wave function leaks,
Yes.
do we also call that phenomenon as also transmission?
No, because transmission is what I would have asymptotically, far away. As x tends to plus infinity, then I expect the potential to go to constant and the wave function to become just a plane wave with some effective wave number. Okay. But if it is finite in there, no, but then if the barrier is finite and has a finite height, you see it does get transmitted, it will get through. Even if the energy was less than V naught, it would still happen because once it is on the other side it would be again a plane wave. It is only if that potential barrier goes all the way to plus infinity that you have an exponential cutoff. If it is finite, then there is a plane wave back once again, and this particle can go through, can get through. It is exactly like a light wave traveling through a heavier denser medium. It does get through and get transmitted. Okay. Now let us look at the problem of a particle in a, I would like to do this in an electric field and then in a magnetic field, which is a little more complicated, but an electric field, as you know, the simplest electric field is a uniform electric field completely, in which case the potential is just a linear function of x because the force is constant, charge multiplied by the magnitude of the electric field. So let us look at first a particle in a constant force field. And what I have in mind is something where the force is constant, some capital F for example. So V of x, again one dimension, is equal to minus Fx. F is a constant. Therefore minus dV over dx is the force F. Okay. What kind of potential is this? What kind of shape is this? Plot V of x, what does it look like? It is just a straight line. If I take f to be a positive number, it is something like this. Now it is clear that a classical particle in such a potential would simply roll down to x equal to plus infinity, and whatever energy you give, if you give it an energy of this much, it can go up to this point on the x axis, it can climb up this barrier and go up to this point, but it can't go to its left, and then it would die down. It would get reflected back. That is what a classical particle would do, and the spectrum of the energy in this problem, the Hamiltonian, would be really minus infinity to plus infinity. Any energy is allowed from minus infinity to infinity. So classically it is a completely trivial problem. Now quantum mechanically, what do you expect? What would you expect? What kind of energy values you can see? E must run from minus infinity to infinity. In this problem, minus infinity less than E less than infinity, and there are no bound states. There is no confining potential. So there are no bound states in this problem, and it is not normalizable, the solution is not normalizable, but what kind of wave would it be is the question. What would you expect on this region? If this were your energy, what would you expect? Exactly as in a potential barrier problem, I would expect there will be a little leakage into this, but since this goes all the way to infinity, I would expect it to exponentially die down on this side, and on this side maybe it would do some wave motion. This is what I would expect. This is certainly not bound states, so not normalizable. Now let us see if we can solve this problem. We write down the Schrodinger equation for energy eigenvalues. It is minus h cross squared over 2m d2 phi over dx2. So I am looking at stationary states of the system with some energy E, some given value E. So I should really write phi E of x as the position space representative of a stationary state corresponding to energy E, and E is a continuous spectrum minus infinity to infinity. So for any E I have d2 phi E of x over dx2 plus the potential, and the potential is minus fx phi of x, and this is equal to E phi E of x. The quantum number, if you like, in this case n is replaced by E, that is a continuous variable that labels the eigenvalue of the Hamiltonian. This is the equation we have to solve. It is not a trivial equation because of this guy. So let us get rid of the minus signs and so on and see what happens. We have phi E double prime of x plus E plus fx 2m over h cross squared phi E of x equal to 0. Now it is obvious that I should change variables to this guy. It is clear I should put a new variable there, call it C or something like that. So let C equal to 2m over h cross squared E plus fx, and then what does this wave function do? It does, well, in some new variable, let me continue to call this phi itself. So phi double prime of C E plus C phi of C equal to 0. There are some constants, right? Fashion, and so I differentiate twice, I get some f dependent constants which I would move here, so some constant sitting here. That is the derivative of this guy if I differentiate twice. Okay. But this constant does not involve E, therefore there is no reference to E here at all. No matter what the E is, you have exactly the same functional form of the solution. It is independent of E. Right? Now what kind of solutions do you have for this equation? It is a non-trivial equation. This is called Airy's equation. And the solutions are very strange objects. The solutions to this are of the form phi E of C equal to some constant, normalization constant, times the Airy function of minus C. This is called the Airy function, of argument minus c by convention, where the Airy function of some variable z is equal to 1 over root pi integral up to infinity du times cosine of 1/2 u cube plus uz, some strange object of this kind. It is a special function, it is tabulated, but it is a solution of y double prime plus x y equal to 0. It is a weird function, got some oscillatory stuff integrated and so on and so forth, not integrable in terms of elementary functions. So this is not very transparent, although this has been well studied and people have found the asymptotic form and so on. The reason is I have chosen a very bad representation to work in. In this problem it would have been easier to work in the momentum representation, because you see the Schrodinger equation become much simpler in the momentum representation. You have h phi e of p equal to e phi e of p in the momentum basis, and the Hamiltonian is p squared over 2m minus f times x. But what is x in the momentum representation when acting on phi e tilde of p? Plus IH cross d over dp with a plus sign. So this would become very easy. That is the momentum space equation. Well, that is easy to solve. That is much easier to solve because it is a completely trivial equation. Right? I do not have to write the solution down. It's got constant coefficients, and it's immediately separable and integrable. Moreover, it has a great advantage that it's a first order differential equation. So simply move this guy to the other side and get rid of the minus sign. So take this out here and then put E minus p squared over 2m phi e tilde of p. So it is E minus p squared over 2m acting on that guy is this equation. I by h cross f, that is it. It is a trivial equation to integrate. You just have to do integral p squared with respect to p, and that gives you a p cubed, and then the other term will give you an EP, and therefore you are going to get a solution which is going to look like phi e. I will ignore the signs and so on. This is of the form some constant times the exponential of IEP minus p cubed over 3 or whatever it is. So as far as the p dependence is concerned, it is going to have a linear term and then a cubic term multiplied by various constants. So the Fourier transform of the Airy function is quite straightforward to write down. Incidentally, that is why this u cube turned up here. It is related to the fact that you got a p cube there. Okay. What does this function look like is a question, and it is possible to do asymptotic analysis. And it turns out that as I tends to minus infinity, I expect the wave function to actually die down. Remember, xi was just proportional to x here. So I expect the wave function to die down on the left hand side. So I expect on this side something to die down, but on this side I expect some wavy object like this, and this is what this Airy function does. As I tends to minus infinity, the wave function phi tends to e to the power minus mod xi to the 3/2. It dies down like e to the minus mod xi to the 3/2 on the left hand side, faster than exponential. On the right hand side, on this side it remains wavy, but the amplitude dies down very slowly. So xi tends to plus infinity, phi goes like xi to the minus a quarter times a sine function of something or the other involving psi. So something oscillates but with a very, very low amplitude, and you can find this constant that multiplies it by normalizing it. Now since these are not normalizable wave functions, because there is no discrete spectrum, you normalize it in momentum space, you do an energy normalization. In other words, it is reasonable to expect that both in position and momentum space I have the following normalization. So a wave function of energy E and a wave function of energy E prime should have an inner product which is proportional to a Kronecker delta E minus E prime. So the normalization condition would be dP minus infinity to infinity phi E of P tilde phi E prime tilde of P should be equal to delta of E minus E prime. This is the normalization condition that I would put on wave functions which are not bound states, which are not normalizable in position space. I simply say that the eigenvalues, eigenfunctions of the Hamiltonian form an orthonormal set, and it is a continuous spectrum, so it is reasonable that that is the normalization condition. A similar one in the position space. That will fix your constants, so I leave you to work out the rest of it. It is easy to find phi E of P subject to this normalization condition. This solves now the problem of a particle in a uniform field, of force. Yeah. Pardon me? Sorry. You are right. Right, absolutely. Yes. Oh yes. Unlike bound states where the wave function could be made real, that is no longer true here. There are these e to the I k x's and so on, so the wave function is a complex quantity, and this is called energy normalization. Okay. So that fixes the problem in a uniform field. Now if you put a hydrogen atom in a uniform electric field, you have what is called the Stark shift. Well, that is a 3-dimensional problem, but again you would have a similar thing. You have a potential which is a 1 over r, that is the Coulomb potential due to the nucleus. On top of it, riding on top of it, if you put a field in the z direction, you would have a potential proportional to z. This actually makes the problem much more difficult to solve, because on the one hand 1 over z does not have spherical symmetry, so you lose the spherical symmetry, and then it is not clear what would happen to the energy levels formally, because this potential actually becomes unbounded. It is not a confining potential anymore. We will mention this when I will mention this when I talk about the central force problem. Okay, I will come back to it. Now that we have seen what happens in a constant electric field, let us see what happens in a magnetic field. I put a magnetic field and look at a particle moving in a 3-dimensional space. This is a more non-trivial problem. So let me write particle, charged particle, of course, in a constant. Let us look at a constant magnetic field. This is going to take some time, so I just set the preliminaries up today and then we will resume this thing. Let us go right back and ask classically what happens. Now when you do quantum mechanics you need to be able to write the Hamiltonian down. So first let us ask what happens classically. I put a particle, a charged particle in a magnetic field, classically what happens, and I need to know the Hamiltonian formalism. Now you know that just to recap, to remind you of what went on, the Lagrangian of the particle classically was 1/2 mv squared, that is the free particle, then you put it in a magnetic field and then you have E times, E is the charge of the particle, A dot V, the vector potential, and then if there is a scalar potential that term contributes to, and you have an E phi where this is the vector potential and that is the scalar potential, and they are functions of r and t in general. But if you have a static magnetic field then you can switch off phi, the scalar potential, and you have some A which is a function of r alone, but this is true in general. And from here you would go to a Hamiltonian by going through first a momentum, and the canonical momentum that you define is P equal to delta L over delta V, the derivative of the Lagrangian with respect to the generalized velocity, and this is equal to mv plus Ea. So the canonical momentum is not the mechanical momentum, it is not mass times velocity, but involves the vector potential as well. Therefore when you put that in, you go to a Hamiltonian which for the free particle was p squared over 2m for the free particle, but the moment you put in a magnetic field this potential is replaced by p minus Ea whole squared over 2m plus E phi. So if you recall, this is all that happens where p is the canonical momentum. And now we are working with a constant magnetic field, so we do not have a scalar potential, we have this guy here, and what we have to do is to take this as the quantum mechanical Hamiltonian where p is the momentum operator. So now our quantum Hamiltonian is H equal to P operator minus E operator, but that could be a function of position in general, A of r squared over 2m. Okay. Now we got to be careful because we know that P and A do not commute with each other. May not commute with each other in general because A is a function of r. Therefore you are going to have, when you square this guy, you are going to have terms which depend on p squared over 2m, but there is going to be a p dot A as well as an A dot p term, and they do not commute with each other. Classically you do not have this problem, but quantum mechanically you do have this problem. So you want to know, finally you will have to compute, there is a p dot A, and then you want the commutator of p dot A with A dot p, and therefore this is p of A of r minus A of r dot p. We have to compute this number. Pardon me? Well, if I take the square of this vector, it is this vector dotted with itself, right? So there are going to be terms p dot A dot p, or write it otherwise in Cartesian components, the square of px minus Eax, etc., etc. But the fact is p and A do not commute, the Cartesian components of r and p do not commute with each other, the same Cartesian components. So we really need to address the question of what is this commutator, because if I know that, then I can write everything in terms of p dot A dot p is given in terms of p dot A. Now what is this equal to? Well, this is like asking, I can do this in 3 dimensions, but it is like asking what is x with p, one Cartesian component x with px, this is IH cross times the unit operator, and then the question was what is f of x with px, What is f of x with px? IH cross times f prime of x. So this is equal to IH cross f prime of x. Therefore one can write this down. This is equal to, oh I got a p first rather than an x first, so I must put a minus sign to start with so I do not make a mistake, and then an IH cross is going to appear here, except it is in 3 dimensions. So instead of what will I get? It is a dot product. So this is going to be divergence of A, del dot A of R. You can go through the components and so on, but it is equal to this guy. So as long as del dot A is not 0, you are in trouble, but now of course you remember from classical electromagnetism that you can always work in a gauge in which divergence of A is 0, and what is that called? It is the Coulomb gauge. So we can always work in a Coulomb gauge, and this guy is 0. You must be careful though. Now let us look at our problem. Our problem is to put a magnetic field B, and that is equal to, sorry, I want a constant magnetic field B. The A of R for a constant magnetic field B in some arbitrary direction. Not surprisingly, since the curl of A must be B, A must be a linear function of the coordinate, so that when you differentiate it you get a constant. And what is the solution? Does anyone know what the famous representation for the vector potential is? Curl A equal to B, but B must be a constant given vector. So what is A in terms of B? Such that when you differentiate you end up with this. This is equal to half B cross R. So I urge you to work this out, check this out, this elementary vector analysis. If you find the curl of A, you discover it is exactly equal to B. This is the inversion of the equation, curl A equal to B, so A equal to half B cross R, if B is constant. Is the divergence of this 0? We got to check. We got to check if the divergence of this is 0. I assert that it is trivially 0 because del dot A equal to del I AI in tensor notation, this is equal to del I, and AI is half B cross R, so it is equal to epsilon ijk Bj xk, and B is constant. So this guy comes out Bj and I leave you to check out that this in fact goes to 0. So the divergence is 0 and therefore you are in shape equal to 0 P and A commute. So that complication is off our hands. The next thing we got to worry about is how do we make sure that the entire thing is independent of arbitrary gauge transformations on A, because there is nothing sacred about A. I could choose instead of A, I could choose A prime is A plus the gradient of any scalar function of the position, and it will not change the curl of A, which is B. So no physics is changed if I add a gradient of a scalar function to the vector potential. What will happen to the Hamiltonian? It will change, but it will be a canonical transformation. Nothing will get affected, but I must make sure that the Schrodinger equation does not change. I must make sure that this equation H psi, or for the eigenfunctions it would be H phi equal to E phi, I must make sure that this equation does not change. And next time I will tell you how to do this. You need to introduce a phase factor into the wave function. So along with the gauge transformation for the field, you also have to make a transformation on the wave function, and it is a package deal. Then you are assured that the system is gauge invariant. this phase factor will not be a measurable quantity, it will be arbitrary, not a measurable quantity, because physical quantities will depend on phi star phi and this phase factor will cancel out, except in some very interesting situations where the space you are working in is not simply connected. If there is a flux line passing through, for example, and then you do have a quantum non-integrable phase, and this is the start of the so called geometric phase theory or non-integrable phases in quantum mechanics. The very famous effect called the Bohm-Aronoff effect, which I will talk about and tell you how it arises from the phase factor which you need to put in on phi in order to preserve gauge invariance. Okay. So we will do this. The next thing we will look at is the velocity operator, because we also have to ask what happens physically to the velocity of this particle, and it will turn out that the different Cartesian components of the velocity do not commute with each other, although in momentum would. So that is one more indication why the momentum is far easier to handle than the velocity. So let me do that next time.